Okay, if momentum is affected, therefore energy could also be affected. Let us check this one. After derivation, we now have that the kinetic energy of an object is equal to the difference between the gamma mc squared and the mc squared, wherein let us recall that the total energy is the gamma mc squared, and then the total energy is equivalent to mc squared plus the kinetic energy of the object. Recall also that the mc squared, that is the rest energy of the system or of the object. Okay, so take note of that. That was the discovery of Albert Einstein. So E naught, or the rest energy, is equivalent to mc squared. Now let's derive the relationship between total energy, rest energy, and then momentum. Take note that we were able to derive an equation for energy is equivalent to mc squared divided by square root of 1 minus v squared over c squared. Now let's take a look at this and then square both sides. E squared equals m squared c to the fourth divided by 1 minus v squared over c squared. Okay, so that will be our expression for E squared. And then take note also that we have an equation for momentum. Earlier, we have P equals mv, okay, wherein mass is a factor of velocity, 1 minus v squared over c squared. Now, what if we have an expression wherein we have p squared c squared? Okay, let's square this one. Let's square momentum. This is the equation for momentum, wherein mass is affected by the velocity. Then you have here, let's square momentum. We now have m squared v squared divided by 1 minus v squared over c squared. So this expression is p squared. Then let's try to multiply it by c. This is p squared. Then let's try to multiply it by c squared. So you now have m squared, v squared, c squared divided by 1 minus v squared over c squared. So looking at this equation, okay, so let's take a look at p squared, c squared, where we have energy squared minus p squared, c squared. Let's take a look at that. Let's try to subtract total energy, E squared. Okay, now let's try to subtract the expression p squared, c squared from E squared. So you have E squared minus p squared, c squared. Okay, let's continue on the next slide. Alright, again we have E squared minus p squared, c squared. Okay, so we now have here energy squared equals m squared c to the fourth divided by 1 minus v squared over c squared. And then we have, for minus momentum, we have m squared divided by 1 minus v squared over c squared, and then v squared. Then of course we have the c squared. Okay, so let's subtract this one. So you have here, based on your basic mathematics, you have the least common denominator, or the LCD. We can have 1 minus v squared over c squared. 1 minus this divided by this is just 1. So that will be m squared c to the fourth. And then 1 minus this, or this one divided by this equals 1. So that will be minus m squared v squared c squared. Can we cancel out anything or factor out anything here? So looking at the illustration, looking at the equation, we can factor out m squared c to the fourth. Okay, let's try to factor out m squared c to the fourth. We have here m squared c to the fourth. So that will become 1. Dahil tinransfer ko na siya outside. So this expression will just become 1. So upon distributing it, it will just become m squared c to the fourth. So I will no longer write m squared. And then this is only c squared. So we have to have b squared here over c squared. So that upon distributing this, it will still become b squared c squared. Okay, so you're not changing the equation. Then divided by 1 minus b squared over c squared. So you can see here that we can now cancel out this. Okay, let's cancel it. Let's use a different color. So you can now cancel out this one and this. So e squared minus p squared c squared is equivalent to m squared c to the fourth. Or it can also be expressed as m c squared then squared. Okay, so let's finalize the equation. We now have e squared minus p squared c squared equals quantity mc squared squared. Okay, let's write it down. So we can now write it down as e squared minus p squared c squared is equal to m squared c to the fourth. Or we can also express it as e squared minus or equals m squared c to the fourth plus p squared c squared. Or e squared, we can have m, quantity m c squared squared plus p squared c squared. Okay, in the derivation that we had, we are able to derive this equation. The equation above, you can see here, e squared equals quantity mc squared squared plus p squared c squared. Now what if the object has no mass? So does it have energy? This equation will answer that. Looking at this, the mc squared, if mass is equal to 0, so that expression mc squared will become 0. And we will have an energy equals Pc. So what is that? For example, we have photon. Photon has no mass, but take note that it still has energy equivalent to P and, or equivalent to the product of P and C. Try to solve problems on relativistic momentum and relativistic energy. Okay, so let's start. Okay, so let's solve sample problem number 1. A stationary body explodes into two fragments, each of mass 1.0 kilogram, that move apart at speeds of 0.6 c relative to the original body. Find the mass of the original body. Okay, in our equation, we have the rest energy E naught equals mc squared, gamma mc squared. But in the problem, we have here the exploded into two fragments, each having a mass of 1 kilogram. So we have two fragments. So let's consider gamma mass 1 c squared plus gamma mass 2 c squared. So let's now substitute the given. We have for gamma, we have 1 over square root of 1 minus v squared over c squared. Then we have mass 1 c squared plus 1 over square root of 1 minus v squared over c squared. Then we have mass 2c squared. So here, they have equal masses wherein mass is equivalent to 1 kilogram. And then they also have the same velocity, so we can combine them. We now have mass 1 natin ay 1, then the other is 1. So 1 plus 1, that would make 2. Okay, we now have 2c squared. Square root of 1 minus v squared over c squared. So let's substitute. We now have 2. 3 times 10 to the 8. Meter per second squared squared divided by square root of 1 minus, the velocity is 0.6 c. So that will just become 0.6 squared. So let's solve it. Okay, so the mass here is equivalent to 2.5 kilograms. Okay, this is when we say that when we added the masses, it will not be exactly equal to the sum of the two fragments. Like for example, we have there 1 kilogram, 1 kilogram. We are expecting that the original mass was 2.0 kilogram. But for relativity or for the rest mass, they are not equivalent since part of the mass was converted to energy. So that's why we have here the rest mass is equivalent to 2.5 kilograms. So calculate the mass of an electron when it has a speed of 4 times 10 to the 7th meters per second in a CRT of a television set and B 0.98 C in an accelerator used for cancer therapy. So let's solve first for the mass. Okay, the mass of the electron, rest mass equals 9.11 times 10 to negative 31 kilograms. So you have here, okay, the mass is equivalent to gamma times the rest mass. So our gamma is 1 over square root of 1 minus v squared over c squared times the rest mass. So let's just substitute 1 over square root of 1 minus 4 times 10 to the 7 divided by 3 times 10 to the 8 squared times the rest mass, which is 9.11 times 10 to negative 31. Okay. So solving it using your calculator, you will have an answer of 9.19 times 10 to negative 31 kilograms. Okay, so let's have here the mass again. Okay, we have here mass is equivalent to gamma m naught, so that is m naught divided by square root of 1 minus, let's have v squared to be 0.98 c squared divided by c squared. Okay, so we can cancel out c squared. So that will give us, okay, solving this further, that will give you 5.03 m naught. So when it approaches the speed of light, which is 0.98 c, the rest mass or the mass will become 5.03 times its rest mass. So if we have the rest mass is 9.11 times 10 to negative 31, just multiply it by 5.03 and then you will get the mass. Okay, so let us solve this one. An electron with a mass of 0.511 mega electron volt per c squared. So the mass is expressed in mega electron volt per c squared and a photon mass equals 0, both have momenta of 2.000 mega electron volt per C. Find the total energy of each. Okay, based on our derivation, we have energy equals m squared c to the fourth. Alright, that is E squared equals m squared c to the fourth plus p squared c squared. So we can now have energy equals the square root of m squared c to the fourth plus p squared c squared. So we just have to substitute the given. So the mass is 0.11 mega electron volt per c squared, but we have to square that, then c to the fourth. So you can see here that c can be cancelled out, plus, okay, we have the momentum is 2.00 squared. So that is mega electron volt also. Mega electron volts per c, then you have to square it, then c squared. So we can cancel out c. And the final answer for the energy of the electron, so the energy is equivalent to 2.064 mega electron volt. Okay, so this is the total energy for the electron. Okay, so let us continue solving for the photon. So take note that the mass of the photon is 0. So it's a massless particle. So the energy is just equivalent to the square root of p squared c squared. So that will just become pc. So the answer is just 2.00 mega electron volts per c and then multiply it by c. So the answer is just 2.000 mega electron volt. Okay. So that's now the total energy of a photon. Okay. So I think you can now answer the problems in the module. Okay, so before we end this lecture, let's review first, or let's emphasize on what do we mean by rest energy. So the rest energy E naught equals mc squared. That means that an object, even though if it's not interacting with other object, it has this rest energy. For example, burning a coal, if you're going to check the mass of the coal after it was burned, and also the oxygen used, it is not necessarily equal to the rest mass, because portion of the mass is converted to energy. Okay, it's like potential energy. Having a mass means you have this potential energy. So mass also stores energy. Now, as I have mentioned, it doesn't necessarily mean that, for example, a certain object, when they break into fragments, when you add all the fragments, the mass will be exactly equal to the whole mass or the whole object. Okay, so the rest energy or the rest mass is also higher than the sum of the masses of the fragments. Okay? However, it is not usually observed because the decrease in mass is only 1 part in a billion. So it's a very, very small decrease in mass. Another example. If we are going to consider an iced coffee and a hot coffee actually will have a higher mass compared to the iced coffee. However, it will be very, very small that we could no longer observe it. As I have mentioned, it is only 1 part in a billion. Okay, again, to reiterate, the mass of an object is not necessarily equal to the sum of the masses of its parts. Okay? So that is what we mean by rest energy and rest mass. Okay, so another thing that we have to emphasize from the equation, Einstein's equation of E equals mc squared, c squared equals E over m. So this can also be interpreted as the ratio of the energy to the mass of the object. So with this mass, how much energy will be produced, okay? So this is also an equation for, or a formula for conversion of mass into other forms of energy. So take note here that c squared is equivalent to 9 times 10 to the 16 joules per kilogram. Okay, so we also have to give emphasis on relativistic momentum. That relativistic momentum, we were able to derive that is equivalent to mass times velocity divided by square root of 1 minus v squared over c squared. Or we can also express gamma, the 1 over square root of 1 minus v squared over c squared could be expressed as gamma. So we have relativistic momentum is gamma times mass times the velocity. So you can see here that if this one approaches the speed of light, so this is less than 1, okay, 1 minus the factor less than 1, and then 1 divided by a number smaller than 1, that will be a higher number. So that means relativistic momentum is actually higher than the momentum when the object is not approaching the speed of light. So there was an increase in momentum. As we have mentioned, that was attributed to the mass or the relativistic mass of the object. Okay, everyone, so we will end with these concepts and then we will move to another branch of modern physics, which will be quantum mechanics.